OpenAI have released their open source OSS series of models. I'm going to go through the performance of these models and I'll show you how to run inference, how to set up a GPU and hit an endpoint. I'll also talk through how to do fine-tuning with a basic notebook and then a more advanced notebook. Now, there are two models that have been released. There's a 20 billion parameter model and there's a 120 billion parameter model. Both of these, though, run on a single GPU, a H100 GPU with 80 gigabytes. And the reason is because these models incorporate quantization within their training. So many of the weights are stored not in the conventional 16 bits, but just 4. And this allows models that are huge in size to fit on relatively small amounts of VRAM. Furthermore, these models are called mixture of experts. This means that of the total 120 parameters, not all of them are used when you do a forward pass. Only a portion are used, about 5 billion parameters in the larger model case, and about just under 4 billion parameters in the smaller model case. So this means the models should perform at a speed that's closer, not quite the same, but closer to much smaller models that are just 4 or about 6 billion parameters in size. So that means they're powerful models because they have a lot of parameters, but they're also fast because they only activate some of those parameters on the forward pass. I always like to go to artificial intelligence to check out the relative performance of the models. Right now, the strongest model is Grok 4, O3 Pro at the same level, O3 very close behind, and then O4 Mini. And you can see that the open source model from GPT from OpenAI is already appearing here. It's scoring 58 compared to 68, but it's up there with Gemini Flash Reasoning. It's up there with DeepSeek, the latest release from May as well. The smaller model is also appearing. It's outperforming GPT 4.1, which is one of OpenAI's leading non-reasoning models. It's a proprietary one. So you can see the performance here, 51, even of the smaller model, is really not that bad. Interestingly, the largest model is not performing the same as Qwen 3's largest model. Granted, Qwen 3 is quite a bit larger as a model. I suspect if OpenAI trained a model that large, they would have achieved possibly similar performance. So the frontier for open source is still being held by a Chinese lab, but OpenAI here have released a model that's very powerful and also very fast. Now, I'm going to show you how to run inference, first of all, on these two models by running an endpoint, and then I'm going to do fine-tuning. Just something I want to talk about first is this idea of quantization. You'll have heard of quantization before, which is taking a model and usually after training, re-representing it with less bits, with less information. And this tends to degrade the quality of the model a little bit, but often you can do quantization without losing too much while reducing the size of the model. But what's interesting here is OpenAI has decided to train the model with quantization in the multi-layer perceptrons. There are two parts typically in every layer of a transformer. As a reminder, these GPT models, they consist of multiple layers that are stacked on top of each other. Each layer has typically got attention and multi-layer perceptron component. The attention component is where each token pays attention to previous tokens in the sequence. This helps it to develop relationships to predict the next token. And then the multi-layer perceptron is typically just a forward feed. There's no interaction between the previous tokens. So you have two parts, you have multi-layer perceptrons and attention. And what OpenAI have done here is, instead of using all of the parameters for multi-layer perceptrons, they chop it up into experts, and they only activate a specific expert that's chosen when you do a forward pass. And this is what allows them to have a large amount of parameters, but only use one or a few of the experts at a given time. Now, when it comes to quantization, there are a few data types. I won't spend too much time on this, but typically models were historically trained in 32 bits, and more recently that moved to 16 bits, particularly with the BrainFloat 16 data format. And these bits need to represent a few things. They need to represent the sign. They need to represent the mantissa, which is the original portion or the early portion of a number, and then the exponent. So for example, if you had 2e3, that would be, you have this number here. Now I'm not writing it in binary, but 2 would be the mantissa, and then 3 here would be the exponent. So when you have a number, you need to represent a few things: the sign, the mantissa, which is kind of the leading numbers, and then the exponent. And with FP4, which is a 4-bit data type, you would typically have 1 bit for the sign, you would have 2 bits for the exponent, and then you would have 1 bit for the mantissa. And this is the data type that's been used for multi-layer perceptrons in the OpenAI model, so MLPs. Whereas I think for the attention, we're still using, when I say we're, I mean OpenAI are still using 16 bits, probably floating point or bfloat 16. Now, there's another twist here, which is that not just are OpenAI using the floating point 4 data type, they further address one of the issues with quality degradation. So typically, if you use such a small data type for representing each parameter, you're going to get bad quality. And one way around that is to group all of your weights. So group the parameters, put them in groups of either 16 or 32. And within each group, allow for some rescaling. So you might have 16 different numbers. I'm not going to do it with 16, but let's just say you had 4 numbers. Maybe you have numbers 1, 2, 5, and 6. What you would do for this little group here is you might have a scaling factor that you would store. So stored in 16 bits, and it might rescale by, in this specific group's case, maybe it rescales by 17 or something like that. But the whole idea is that you store groups in low precision, just in 4 bits. I know I haven't written that in 4 bits, but you store numbers in low precision, and then you use a scaling factor to scale up and down that group so that it has a larger dynamic range. So basically OpenAI is taking this FP4, and then it's using this dynamic range with groups of 16 or 32 so that you're getting extra accuracy in the dynamic range that makes up for the fact your data type is very compact. And because they do this, they get incredible compression in the model, roughly a factor of 4, because even though the attention is not compressed by a factor of 4, most of the parameters in the model are in the multi-layer perceptrons. So you can actually see that here in this chat I had with ChatGPT. I think I should be able to find a quick write-up. Here we go. So the mixture of experts, which relates to the MLP, this is like 19 out of 20 billion parameters roughly. And so you're getting a factor of 4. Well, it's actually not quite a factor of 4 compression because you need to also store that scaling factor. But you get nearly a factor of 4 compression on most of the parameters. So instead of the model, which is 20B, being about 40 gigabytes if it was in 16 bits, you can kind of squeeze that down by a factor of 4 down to around 10 gigabytes, so 9.5. And then you have the attention and the embeddings. These are not being quantized. They're not being stored with smaller data types, but they're taking up much fewer parameters. And so your total is coming up with around 20 billion parameters. And the same method is being used for the 120 billion parameter model. So in principle, that should take 240 gigabytes, but in practice, it's taking roughly half of that. So it's able to fit on a H100, which is a single GPU that I'm going to show you how to run inference on. So this is kind of the core to why it's able to be small. And then you can see the performance is really good. Why is the performance good? Well, this is probably where some of the secret sauce is, but clearly high quality data is one important aspect. And the other is doing rounds of reinforcement learning. I'm sure the same techniques that are used in O3, O3 Pro and O4 Mini are being used here. So you have reinforcement learning where you are running multiple loops, verifying answers, and then using that reward to update the weights of the model. So that's it for a quick overview. I'm going to show you now how to run inference on this model. And I've set up some one-click templates. They're available publicly if you go to one-click LLMs. That's Trelis Research / one-click LLMs. And you can just look up GPT OSS or look up OSS, and you'll find the 2 models here. All you have to do is click on one of these links. They are affiliate links, and then pick a GPU. Now, they will not run on Ampere GPUs. They will not run on Turing GPUs, the older architectures, because they do not support Flash Attention 3. Currently, the kernels are written with Flash Attention 3, which allows for a fast form of attention, but Flash Attention 3 is not supported by the older GPUs before Hopper. So I recommend running a Hopper GPU. You can run a H100 SXM. You could run the PCI one here either. SXM should be a little bit faster. So you click here. If you want, you can check the template. Basically, it's using this VLLM GPT OSS Docker image. It's then selecting the model. You can select a max model length. Make sure to run on port 8000. I think if you don't specify, it will anyway run the endpoint on port 8000. And then you need enough space on your disk for the weights. That's probably a bit much, but just to be safe. So with that, you can, well, I didn't set any overrides. You can just click here and deploy on demand, and your pod should spin up. Now I've got the pods running here. I've actually run the 20 billion parameter one, and I've also run this here, the 120 billion parameter one. And if you want to just directly hit the pods, all you need is this pod ID, which allows you to hit the pod through the endpoint, through a proxy that RunPod provides. And if you click on this question mark here, you'll see a little README where you can copy the command and just run it. All you need to do is replace this pod ID here. So I've copied the command. I'm going to go off screen here for a second just to paste it into another window. And I'm going to then take this pod ID. And if I open up a terminal, which I have here, let's just increase the size a bit. I can copy in that command. And note that I'm hitting the chat completions endpoint with the 120B model, and I'm asking for the square root of 1678. I'm running with a temperature of 0. And I think that's not recommended, actually. I think a temperature of 1 is recommended. So, wow, that was really fast. I suppose it's only activating 5 billion parameters. So the finish reason is stop, which is a stop token. You can see here the assistant content is provided. But also you have reasoning content, because this is a reasoning model here. So you can see it's going through all the steps. And then this is inverted. So it's providing the response in the opposite order that it actually is generated. It's actually generated the reasoning, and then it's giving the square root here. And this number is correct. You can check it, but this is correct. So yeah, this is pretty much hitting the VLLM endpoint. And even though it's a massive model, it's really fast. So that's pretty beautiful. You can also choose to hit the other endpoint. I can just, let's see, swap this in here. Go back and paste. And what happened? Yeah, I need to adjust actually the model that I'm hitting. It's not the 120B, it's the 20B. So just copy that there, paste. And this should get it right too, because I tested it earlier. Let's see what happens. All right, gives a bit of a longer response, and it's giving here. Yeah, so looks pretty good. Pretty amazing. Pretty amazing. I mean, when I say pretty amazing, there are other open source models that can do this too. It's very nice how fast this is though, because it's using mixture of experts. So that is how to run inference. If you do want to run a fine-tuned model, I'm going to show you the fine-tuning now. It's best if you just edit the pod and put in the slug here for your Hugging Face model. So you have a custom model, you push it to Hugging Face, and this is where you would put in the slug, and it should work nicely. Okay, so with that, I'm going to show you now how to do some fine tuning. And there are two scripts. I'm going to show you a basic script, and then I'm going to show you an advanced script. The basic script is available for free in the basic fine tuning repo by Trelis Research. You can just go over to the GitHub, and I can recommend starting up, again, an affiliate link, but this will give you a one-click experience where you can start up the pod, do all the installs, and clone the repo. So I'm going to use this template. I'm going to call it fine-tuning 20B OSS. And if you check out the template, I'm going to go through this in a separate video, but basically it allows you to start up a pod that will have an appropriate version of CUDA and PyTorch. It's going to clone the repo that you want, which is basic fine-tuning, register a custom kernel, and make sure that Jupyter is starting up. So I'm going to start up that fine-tuning pod. And I actually have, yeah, that's fine. I have started the advanced fine-tuning pod. So for those of you who are interested, I'll show this in the video. I'll show some more advanced fine-tuning techniques, and you can find those scripts if you go to trelis.com and go to advanced fine-tuning. You'll see here a list of a very large number of techniques, ORPO, GRPO, different techniques, unslot transformers for fine-tuning, and you can find details then. You can find all the videos too about how to purchase access to those advanced fine-tuning scripts. We're going to start off though with the basic script. So I will click here on connect, and looks like my Jupyter service is ready. So Jupyter's up and running. Now, I was planning to show this in Colab, but Colab doesn't have enough VRAM to be able to load the model with a T4 right now. So that's a bit unfortunate. You can't use the free T4 in Colab. But yeah, you can run this. You can run this using RunPod or some other service like VastAI or anywhere you can start up a GPU. So you can see everything is nicely cloned and we're in the repo. This is pretty beautiful. You can click into notebooks, open up the open source notebook here. This notebook is based on a guide, an OpenAI cookbook. So you can check that out there via that link. So first thing, we're going to run some installs. We're going to install UV and use UV to do those installs because it's faster. We'll install HF transfer for fast downloads. TRL is the training library. This is for using LoRa. We're going to only train small adapters rather than the full model. Transformers is what we're going to use for training. Unsloth will release library that will probably allow you to save some further VRAM and maybe get a 2x speed up. But for now, I'm using transformers because that's what there's support for. So we've done that install and we're going to do some training here on a multilingual data set. This is the example in the cookbook. It's basically a data set that allows you to train a model to be able to reason in different languages. It has a few different traces you can check out here for different languages. So say French, it's got the user asking a question in English, but then it's doing the analysis in French. So you can see it's basically training it to control the language that reasoning happens in. Maybe a bit random, maybe a bit spurious. The point is I just want to walk you through being able to run the training. So we've loaded that data set. We've loaded it as, we've loaded the train split. There is no eval split on this data set, by the way. You can inspect the data set if you like. And something that's of note, I'll talk about this in the advanced notebook, is the chat template. It's incredibly complex, but it allows for a lot of things like reasoning, like tool calls, and it consists of not just a section for the assistant response, but also an analysis section, which is really the reasoning. We'll move on though here and just load the tokenizer. So we're going to load the tokenizer. And next we'll load the model. And note that we're loading using this micro batch FP4. And I should have said it's called micro batch because every parameter in the MLP has got an FP4 data type. So it has an exponent and mantissa, but the exponent is then further scaled because it's in a group and that group has got a scaling parameter. So you can think of these groups of parameters as kind of the micro. They're the micro exponents. They each have a micro exponent, but then they have a macro exponent that scales the dynamic range of that group. So here we are going to load the model. We're going to use eager attention. I think this means possibly you could train this on an A100, possibly even on a T4. You would need to move this to float 16 if you wanted to use a T4, but there won't be enough memory. So something to think of there. So we'll load the model and then we'll just check NVIDIA SMI, just tells you how much of the memory we're using up. And then we're going to feed in a message and get an answer here. ¿Cuál es el capital de Australia? What's the capital of Australia? And we're going to run this and print out the decoded tokens. So notice how we're loading about 15 gigabytes of weights. The shard should go onto the GPU. And when we've run this inference, we'll set up LoRa. So you can see when the model's loaded, it's using about 44 gigabytes. So it's definitely fitting on the GPU, but using up about half. And here we have the response. It's very fast. Notice how the reasoning level is actually hard-coded into the prompt. Well, not hard-coded, but it's encoded into the prompt. The knowledge cutoff date and the current date are also in there. And there's a system message too. So you can see here the analysis, and then you can see the answer here. So it's providing the answer in Spanish. So we're going to now train, but we're not going to train the full model. We're going to train the model in, by the way, I should say, you can't, normally you can choose not to load the model quantized when we loaded it here. So you can just comment this out, but that doesn't even make sense because the model is trained as a baseline using quantization. So you kind of have to set up the quantization here. You can't just train everything in 16 bits. Or if you did, you would need a 16-bit set of weights, which maybe somebody will push the Hugging Face, but that will just use more VRAM without any advantage. Okay, so we're going to apply some adapters because we won't train the full model. We'll just train a portion of the model. And here what's happening is we're selecting a rank of 8. So this is the dimension of the small adapters. This is the scaling of the learning rate because we train the adapters at a higher rate than the base model because it's operating in a lower dimensional space where we can move faster. We're going to train all of the linear layers, but actually we're going to sub-select. So we're actually not going to train all the linear layers. We're going to focus on these layer 7, layer 15, and layer 23, and the gate and the down projection. We're actually training the adapters in the MLPs. So this is kind of surprising to me. Typically in a mixture of experts, we would just train the attention, but I'm not sure if this comes from OpenAI, but it's recommended in the Hugging Face guide that you do train the MLP layers. If you wanted to train all, you could just comment this out. I'll talk about that in the advanced fine-tuning notebook. So we'll apply the adapters. We're really training a tiny fraction of all the parameters, 0.07%, because we're just training certain layers and certain modules in those layers. And then we're going to train. So here you can, the learning rate 2e minus 4. It's kind of a high learning rate, but I guess that's appropriate because you've got a mixture of experts and the experts are quite small. So you're using a learning rate that's reflective of the expert size rather than the model size. Gradient checkpointing is saving memory. Normally you would train for an epoch, but here I'm going to speed it up just by training for 2 steps. We will log every step. We'll have a batch size. The virtual size will be 16 because it's 4 times 4. Max length of 2000. And we're going to use a scheduler cosine with minimum learning rate. So we're going to basically decay the learning rate and we're going to save to that folder there. So we've set up the training config and we're going to run training now. Once training is done, then we're going to run inference again. Actually, the way this script works is it's going to reload the tokenizer, reload the model, and then load the saved LoRa adapters. Because when we do this, it actually saves the LoRa adapters and it pushes them to hub. It doesn't push the full model, which is good because they're small and that's going to save time and memory. Then we reload them, we apply them. We actually merge the adapters onto the model, which speeds up inference. And then we're going to run a test and see if it's able to use language reasoning in German. Then there's another reasoning test here. Check if we can do reasoning in French. And then, yeah, that will wrap up what we're doing. If you wanted, you could run this, you could run model.push to hub after having merged, and you would have the full model, which you could then run in VLLM. Okay, so I think have we run inference here? No. So we're going to run out of VRAM if I try to do this because it's trying to load another model. So what you actually need to do is restart the kernel when the model is trained, and then you can run this cell because it's going to reload a new model, and then we can run inference and we can see how that performs. Now, I just need to refresh. Let's actually let inference roll out here. It's loading the shards, it's loading the LoRa, and we should see the response pop up here momentarily. Okay, so here we're asking for the reasoning in German. And yeah, I mean, I only trained for 2 steps. So it looks like the reasoning is not yet in German. Well, let's see. Oh, the assistant commentary is in German. So we do have some effect here on the training. Yeah, it is actually. Ich muss die Frage beantworten. It actually does have this in German. And then the final response, La capitale d'Australia, Canberra. Am I speaking French or Spanish? La capital de Australia es Canberra. Okay, it's Spanish. And then we can try having the reasoning language in French, although I'm asking here a French question. So everything here is in French. Anyway, I'm not trying to show you the accuracy of the training. I'm just trying to show you the steps that you need to take. And I'm going to save that and now just refresh so I can add in one more cell. I'm just going to try out the track IO feature. I haven't tried it before, so no guarantee that this is going to work. Let's see if I can add it into a cell here. Track IO. project Hugging Face. And I need to actually copy the URL like this because it's not the local URL, it's the URL via the proxy. So I'm not sure. I'll need to look into that a bit more. Q7860. So I need 7860 and I need project Hugging Face. Am I going to get lucky? It's not looking good. 7860. Let's just try 7860. Oh yeah, that's not going to work. And it's not going to work because I have not exposed in my pod the ID. So if I wanted to expose that, I would need to restart the pod and I would need to expose 7860 like this. And if I click save, then it should be possible to run it. So I'm just going to say requires port 7860 to be exposed in the run pod template. And I'll say then view with, and then you'd need the pod ID. So it would be something like this. And this here would be the pod ID. Okay. So that's the demo of the fine-tuning, basic fine-tuning. What I'm going to show you now is very similar, but for advanced fine-tuning. So for those of you who have access, you would go to advanced fine-tuning and you would check out this one-click template here, which is going to clone the advanced repo instead of the basic repo. It's very similar. The template is a little more advanced because it allows you to inject your Git username and user email, which will mean that you can do Git status and Git push when you log in. So I've started up that pod for the advanced fine-tuning. I started it up earlier and we can just connect in. This is my pod here. When you do connect in, you're going to see there's a folder called fine-tuning. And within that folder, you'll find the OpenAI OSS Advanced Fine-Tuning. So I'm going to quickly walk through this and just highlight a few more advanced features that I like to add in. The first one is that I like using TensorBoard for logging. Now, Track.io I think is cool. It's a new product, and from Hugging Face, it allows you to basically replace weights and biases. But the benefit, well, the drawback is it doesn't allow you to save logs anywhere, whereas TensorBoard currently allows you to save logs in the logs directory. Now, I think you probably could do it with Track.io too. I guess I'm just used to TensorBoard. I'm used to saving within a logs directory and then git committing those logs so that I have the logs available within my repo and I can compare the performance across different runs. In fact, I think I might have TensorBoard. I can pull up TensorBoard just by taking the URL for this pod and then putting in 6006 here, which is a port I've exposed. And TensorBoard isn't actually running, but I can make it run just by loading the extension and pointing to the log directory, which is logs. And when I refresh here, that should be up and running now. So yeah, you can see a history of all my runs. And the run that we're going to be looking at is this open source GPT run here. So that's one of the first things I like to do is use TensorBoard. I'll talk about that a little bit more below. Moving down through the script, I like to create a validation split. So when I load this data set here, I split off whatever is smaller, either 10% of the data set or up to 32 different rows. And that allows me to track the validation loss to see if I'm overfitting during training. So I've got loaded here the train data set and the validation data set. The train data set should be all of the rows minus the validation set. And then we can also print out, if we want, the validation set. And it should have 32 rows. So if we add in a cell here, val data set, you can see here, oh, there's 100 rows in the validation data set. I guess my logic is currently for 10%, and that's not exactly what I was thinking. I wanted it to be the minimum. So Let's fix that. And yeah, now we've got 32 and 968. So that's great. We'll load the tokenizer. That's the same as before, as I showed you before. Now I want to just inspect the chat template. I'm not going to go through it in detail, but when you load a tokenizer, you can then print out tokenizer.chat template like this here. And it's a beast. It's a beast. It's got a whole section on tools. It's got a whole section. I'm not even familiar with all of the different parts here. But what I've done is I've asked ChatGPT to summarize, and there are a few things here. So there's the model metadata. We already saw this in the basic notebook. The model identity, the knowledge cutoff, the today's date, and the reasoning effort are all injected. There's a set of, there's some information here around tool rendering. There's the message rendering logic. There are these channels. So when you're providing a message, that message can be of analysis type, but it could also be commentary. It could also be final. Final refers to the final answer that's going to go back out. So this is quite elaborate in terms of chat templating. Fortunately, it's all been managed by transformers, so we don't have to worry about things too much. We just apply the template. Okay, so if you want to inspect that more, I've kind of left it there. We then apply the template to the conversation, nothing too different here. And then we're going to prepare the model, which just involves loading the model. There's nothing different here either. We're doing everything the same as before. Run NVIDIA SMI and run a quick example. So we've asked a question, we get back an answer. Now, I've made one change here, which is that rather than only train specific parameters, and I should just reload the model, I think. Rather than train specific parameters, we're going to try and train all of the linear layers. So we're not going to limit it just to, the up and down projections. And what that should result in is training a larger number of parameters, which potentially can help with accuracy. So we can see now as I think the model is still loading. Well, the model is loaded. We're actually close to capacity here. And the reason is because I probably have two models loaded now, because I had a model loaded and now I have another model loaded, which is not maybe ideal. We're just about to do some generation. And maybe it would be wise at this point to just restart the kernel and run all cells. There's one small change here I've made actually on the Hugging Face login. If you want to push the hub, you need to be logged in. What I like to do is wrap this in if hffolder.getToken is none. Basically, it means if you keep restarting the kernel and running the script, it's not going to ask you to log in again if it already sees there's a token that's present. Okay, so I've restarted the kernel. It's going to reload the model, and you can see now that the GPU is only about half full, which is better. There's not two copies there. You can see we've got an output from the model. And okay, we still have a small number of trainable parameters. So what I'm going to do here, let's just stop. It's probably we're training. I want to print the model and see what's in there. So I can see there's attention, qproj, kproj, vproj, and then there's the MLP, which is here. And I actually don't see up and down, which is interesting. MLP.experts. So actually the up and down are wrapped within the experts, which is kind of interesting. So I think what I want to do is I want to comment out the target parameters. I want to train the attention. So target modules equals, and I'm going to put them in a list like this. oproj, and I want vproj. This is all the attention, so I want oproj, vproj, kproj, qproj. That means projection. And I'm missing kproj. Kproj. And I also do want to train this. And I also want to train this. And I think I can do this. I think I can do this just by passing like this here. I'm not entirely sure, but I think I can do it like that. And I'm actually going to have to, I don't think I can rerun that, unfortunately. So I'm going to have to restart and run all cells. Because if I just rerun this cell, it's already a PEFT model. And so I've already applied a LoRa adapter. I think technically you could unload the LoRa adapter and reload it, but I'm just going to take the quicker route of reloading everything. And what we're hoping to see here is that we have a larger number of trainable parameters. So the model's loaded, and we do not have a larger number of trainable parameters. But we can print it and check. So we can ask here, in ChatGPT, give me a snippet to check which modules are trainable. I'll run it after this code. And I'm gonna see what it says. Okay, so print the trainable modules. And okay, so let's check. We have the Q, we have the KVO, and it's showing all of the layers. And it looks like, so this is good. I mean, the trainable parameters are just small because our our rank is small, and there just aren't many parameters in the attention. But what I suspect is I may need to adjust this here so that I can get those to be trainable too. And we'll see if that works. If it doesn't, I will move on and I'll leave a comment later on the video. Because I want to discuss some of the final aspects of this training script. I'm just going to put this in here and say, this isn't working for targeting the linear layers in MLPs. Should I instead do something like this? This is a bit of a guess, but my hunch is possibly, see, I'm not sure whether this will subselect. And if it does subselect, then it's going to mean that these attention layers won't actually be trainable, which is not what we want. But I'm potentially guessing that if we can just do something like this, it may work, but we will see. We'll give it one more go. Then we'll move on because I want to talk about some of the training here. A few little things. First of all, we are using an evaluation set. So I'm passing an eval data set equals val data set. I'm doing evaluation. I'm setting the evaluation strategy to steps, which means that when we set eval steps to 0.2, it will run evaluation every 0.2. That's every 20% of the total steps. I have set a logging directory here with the run name that I've specified above. I've also set a hub model ID. This sets the default repository when I push up to hub that the model is going to go to. I've also moved logging steps to be every 5% of the training. So typically here, by the way, I set gradient accumulation equals to something like int divided by the batch size. So if the per device batch size is 4, usually I would make this a variable batch size and put that into here. And then I can set batch size equals to 4 up here. And I will make sure gradient accumulation gives me a virtual batch size of 32. I've set the output directory here to outputs, report to TensorBoard, and allow for pushing to hub with the trainer. So I think we can just do one more check here. If it's, yeah, this is actually what I had. MLP. we can try substituting this in, but I suspect what I had was maybe correct. So I'm going to leave in the old version here. I'm going to just comment it out. And let's take that little snippet here, which can help us print some debug. And we'll run that. So kernel restart and run all cells. And with that, we should have our script running. Once the script runs, it's going to push the LoRa adapters to hub. It's then going to merge the model. If you wanted to additionally push to hub, you do model.push to hub. And then you could put in here the model name. So it could be something like Trelis / run name and full model. Well, could just call it merged, perhaps. That would allow you to push up to merged. And push to. And by the way, the nice thing is because the model is trained with this low data, with this compact data type, the merging is not going to cause problems. Often when we quantize a model and then we try to merge back to 16 bits, we include error. There's some nuanced reasons there, because basically when you merge, you want to merge back to a quantized version of the original model, but we're not losing precision here when we merge. So this is because the model is natively trained in that precision. So that's excellent. Okay, we're out of memory for this model, probably with that number of, yeah, it's probably because I'm now training more parameters and I'm not able to fit. At least that's one of my guesses. Let's just check if that did actually train those MLP layers. And yeah, I don't see the MLP layers in the list. So that is going to require debug to figure out how to train those exactly. I do know one way you can definitely train them is by taking the original approach, where you specify layer by layer, and you could list out more layers if you wanted to. I don't suspect that there is going to work. And if you do all linear, that, yeah, it should allow you to hit all linear plus hit these target parameters. So unfortunately, I haven't really improved with my suggestion here. All I've done is provide you with a way to only train the attention layers and not train these up or down projections. So probably it's better to just use the default. I'm going to say here it doesn't work. So I'll comment out my version and we can just rely on using the version that is already there. And when it comes to training, then it looks like we're running out of VRAM. I think I can rerun it again because I know that earlier I was able to run this with no problem. So let's do kernel restart and run all cells. And we should just check that when the model loads, it's not taking up more VRAM than we expect. Oh, here we go. So yeah, taking up half the memory. You could also run NVIDIA SMI after applying the LoRa adapters. If we use the default settings there for training, you can see that, do we have the MLPs here listed? Should be listed in layer 15, for example. I don't see them. I don't see them listed there. So perhaps it's a listing issue, actually. This probably needs a bit more debugging. I'm just going to adjust my batch size here. So I think the problem is that we're not logging the parameters. Okay. So we have everything listed here. And for the fine tuning now, it should start up momentarily. Yeah. I mean, that's going to show an incredible amount of detail. So if you do run that, I'm just going to put it commented out because it will take up a massive amount of space in a notebook. So I'll just comment both of these out, but leave them as an option. That's only if you want to run TensorBoard. And training should be underway here. And TensorBoard should be available. If we go back over here, we should see a number of runs. Well, it's actually overwriting the same run. So you might want to add a time date stamp if you want to see new data up here. This is a run I did earlier. You can see the eval loss is falling over time, which is good. It means we're not overfitting. And you can see the training loss. It's now been overwritten because we're just running a new run. But the training loss here should be falling hopefully over time. And it looks like we're hitting an out of memory error here. Yeah, it's running out of memory on the eval batch size. And what we can do is just reduce that eval batch size. I can just put that down to be smaller. Even reduce it down to something like that. I think we can still leave in here the 32 over batch size. And unfortunately, when your training stops, you're not able to just rerun it because usually the GPU is in a bad state. So you do have to typically restart, which is a bit of a pain. And I'm going to commit all these changes up to Hugging Face. By the way, if you ever want to connect into the pod, you would just go to connect. You can connect via SSH. So if you go over to a terminal like this, open a new window, and you need to put in the right SSH key, which you should have entered on RunPod, and that should connect you up to the pod. You should be able to go into Workspace, and then I want to go into Advanced Fine Tuning. And I can now do, I need to check actually, CD Workspace. And yeah, I'm actually in the basic fine tuning repo, so that's not the one I want. I want to connect in instead to the advanced fine tuning. So I'm going to just exit and exit. And now connect to the advanced fine tuning pod. And now I'll CD into Workspace and CD into work space, CD into advanced fine tuning, and git status. And you can see here the logs and the updates I've made. So I can now do git add, and this is working because I've set my GitHub username and my email within the RunPod environment variables. I've actually set them as secret first. So here I could add all those files, and then I can commit the changes and push them up, which I will do momentarily. And unfortunately, it looks like we have, now we have an error with batch size because that needs to be an integer. And I'm not sure, maybe I can just run again here. And run inference. And I've just run through the script again. And now with my validation batch size 1/4 of the training batch size as set here, and also using int to make sure that this is passed through as an integer, I've gotten all of the steps to run. And you can see I have then pushed up to hub. If you check out that repo, you can see that there are model weights for the adapters, just 60 megabytes, so very compact. I restarted the kernel, so kernel restart, and I ran inference, and I have the inference examples here. So the full fine tuning script is working well. I'm going to push those updates to advanced fine tuning. And as I said earlier, you can find those if you go to trails.com/advanced-fine-tuning. That is it from the overview of the OpenAI OSS series of models. They're really compact, they're fast, and they're high quality. So I think they'll provide a very good baseline for open source work. You have the two sizes as well, so you can run either something smaller or you can run something larger if you have the VRAM for the higher quality. And it seems like they can be fine-tuned well and run very well with VLLM for inference. So you have the full toolkit available, and I think this is going to be probably the model of choice for now, at least until the next version of Llama or something comes out. Quen, it should be noted, is still outperforming it, which is kind of interesting, but perhaps we'll see a later release from OpenAI where they might go even further ahead with the open source. So that's it for this review, folks. Cheers. Now, as a bonus, I'll just make a few quick comments on what I think this open source release means for what we know about proprietary models. First of all, the move back to mixture of experts has completely made the 180. We went from having mixture of experts with GPT-4 and then going away from that with the Llama 2 and 3 series of models. And then with Llama 4 and also with models like DeepSeek, we came back to mixture of experts. And here it seems we have now fully come back to mixture of experts, probably because of the speed improvement that they allow, but also because model providers have figured out how to balance the experts during training. That was one of the key things DeepSeek figured out, and maybe OpenAI have even better techniques. But the fact that they're able to run such large models that only activate a small number of experts means that they are able to very effectively repartition the information across all of the experts during training in a way that is balanced. Now, we can't examine, well, we can, but I haven't examined the balance and the usage of the experts when we do inference. That would be something interesting to look at, and it might be a way to compare how well OpenAI are able to balance the experts during training compared to DeepSeek or to other companies like that. Note also that Qwen, with their largest models, their most powerful ones, they are also a mixture of experts, and they're a smaller 30 billion parameter model with around 2 or 3 billion activated parameters is also a mixture of experts. Now, it seems from the performance of the OpenAI OSS model that they are using a lot of their harnesses for the reinforcement learning because the reasoning performance is as good as O4 Mini for the larger of the OSS models here. An interesting question is, what are they holding back that is not being used, that is being used in the proprietary models? In some ways, by releasing these open source models, they have kind of overwritten some of the proprietary models like GPT 4.1, which is performing worse even than the smaller open source model on many benchmarks. They've also probably overwritten some of the text performance of models like GPT 4.0. Now, the open source models here don't support images or audio, so that remains kind of a defining dimension of the proprietary models that OpenAI are offering right now. So that's one axis where they haven't fully shared across. One might also guess that the proprietary models are larger. You can see the performance of O3 is outperforming, still outperforming O3 Pro, especially outperforming the larger OSS model. So possibly that indicates a bit of a larger model. And the same then with O4 Mini, it's performing a little bit better, potentially a larger model as well, or potentially adding some splits of data for reinforcement learning that just weren't provided to these models here. Perhaps what's most significant here is that Llama has fallen off of the leaderboard for open source models, and there has been no Western model that is open source. So the most significant thing about this release is the capabilities. Now, at least within the top, say, 10 models of all models, we again see the reappearance of a Western model, and it is a model that is quite fast as well as being game. As usual, folks, let me know your comments below. Cheers.